I'm Terry Klinker. We've talked about the steps in decision making for a model. Now we're going to go into the properties and the assumptions of a model. Now the first thing that we need to understand is we are talking about linear models, or linear programs in this case. Linear. Linear is exactly what it sounds like. It means that it is a variable raised to the first power. All right? X raised to the first power. No squares, no cubes, no square roots. All right? We're keeping it simple. And it's going to be in the form of, all of your variables will be in the form of x to the first. All right? If we have multiple variables, you could have y, z. A lot of times what we'll be doing if we have more than two variables is we'll give them more unique things like x1, x sub 1, x sub 2, x sub 3, all the way out to x sub 254, depending on how many variables you have. Can't stay with letters when we're going to go beyond 26 letters. All right, obviously some of the letters can't be used. O's look like zeros, I's look like ones. So what we end up with is variables raised to the first power. That's linear. All right? So the properties of an LP model. First off, it represents a business problem as closely as possible. So our model is going to represent a business problem. All right? Secondly, our model is going to try to maximize or minimize some quantity. All right? We're maximizing or minimizing a particular quantity. We're trying to maximize profit, maximize revenue, minimize cost, minimize number of employees that we have. All right? We might be looking at a problem where we're trying to minimize layoffs if we're in the middle of a recession. We're trying to maximize or minimize some quantity. It has limitations. These limitations are referred to as constraints. We have limitations. We can't go to infinity. Now, this should seem obvious, but some people don't seem to get it. We have constraints. I have a constrained labor pool. I don't have an unlimited number of people that I can hire in that can work an unlimited number of hours. And if I did, let's say I'm the ancient Egyptians and I just keep enslaving people and I've got an unlimited labor pool, I don't have an unlimited amount of material. And even if I had an unlimited amount of material and an unlimited supply of labor, I probably don't have an unlimited market to sell to. There are constraints that keep me from producing infinity or selling an infinite number of products. And the other property we have here is there must be alternatives available. If you must do it to one constrained solution, then there's no sense analyzing it. If no matter what the solution says, you're going to do it this way, there's no problem. You're going to do what the boss says and you move on. If you have no alternatives, if you have no options, then there's really nothing to analyze here. All right? And the last thing is what we said to begin with. This is linear. It's raised to the first. So this maximizing some quantity, this gets into some of the components that we have. All right? We're maximizing some quantity. We use what's called an objective function. What's our objective? To calculate that maximizing or minimizing number. All right? Maximal or minimal number. So we're going to have one of the components of our program is going to be objective function. We're also going to have something called decision variables. That's these items up here. Decision variables are those variables, those quantities that we have control of. We can control how many of product A we make versus how many of product B we make. Using these, we come up with something called the optimal solution. The optimal solution is the value of these variables that maximizes or minimizes, depending on what we're trying to do, the value of the objective function. So this solution is the value of these variables that maximizes or minimizes the objective function. We also are going to have constraints. These constraints are what we said limits us from doing an infinite amount of work or producing an infinite amount of material, of product. All right? So you'll want to be a member of these 4 phrases. You'll want to know what they mean. You'll want to know how they work. Now, these are the properties. We also have 4 assumptions of linear programs. The 4 assumptions of linear programs, all right, the assumptions we have that go into this: 1, certainty. The coefficients that go into my constraints, the coefficients that go into my objective function, are constant, and they remain constant throughout the entire problem. If they change, we will have a new optimal solution. So what does that mean? Well, if it takes me 10 hours to build a car, it stays 10 hours the entire way through the evaluation period. All right? So we have certainty with the assumptions that go into our model. Proportionality. In a linear function, things are proportional. If it takes 10 hours to build 1 car, it takes 20 hours to build 2 cars, 30 hours to build 3 cars, 100 hours to build 10 cars. It's proportional. All right? We don't see a big savings as we do more. It's consistent throughout. That would, if it took less time for every car as we increase the number of cars, that would not be a linear function. So we have proportionality. Additivity. All of these hours would add up. If it takes 10 hours to produce for every truck, for every car, and 15 hours for every truck, and 12 hours for every van, then I could add up how many hours I spent making cars, how many hours I spent making trucks, how many hours I spent making vans, and it would tell me how many hours in total I have consumed, how many hours of labor I've consumed. It adds up. The last one is the one that gives you a little bit of trouble, and that is divisibility. The solution does not need to be a whole number. All right? I want you to think about that for a minute. It does not need to be a whole number. If it had to be a whole number instead of a linear program, I would be adding the additional constraint that it's an integer program. Changes the program entirely. Why does this give you a problem? Well, if I told you we were building cars and the optimal solution said to build 5 cars, 6 trucks, and 3.5 vans, you would say, I can't build half a van. You're correct, you can't. But we will assume divisibility, we will use 3.5 vans as an acceptable number, an acceptable response in a linear program. I'll talk more about what we do with that later on. We also enter, what if we're talking about labor? If I need 3.2 people, well, I can't have 2 people or 0.2 people. I can't divide people up into pieces. In most of the United States and some parts of Arkansas, you are not allowed to chop people up into bits so that you can have just 0.2 of a person. And that makes sense. It doesn't make sense to you. It drives your little brains crazy. All right? Just accept that a non-integer number, even if it doesn't make sense that you can actually implement it, It's acceptable as a solution in a linear program. We'll continue on with an example in the next video.